Now let's look at generating the tangent function using the Taylor series approximation. So this is the approximation here, and we're going to use the first 4 terms. Now I've got the tan function drawn out here in brown, and I have the approximation in blue from minus pi by 2 to pi by 2. So that's from plus 90 degrees to minus 90 degrees. Now you can see here the tangent function is discontinuous. That is, when we hit 90 degrees, or as we head towards 90 degrees, the function tends off to plus infinity. And then whenever we are just above 90 degrees, the function is at minus infinity. So there's a discontinuity within the function. And you can see here that as we head towards 90 degrees, our approximation here gets worse and worse. Okay, but we're not really bothering about this too much in terms of the approximation method. There are lots of different ways of approximating functions. For our purposes here, we're just going to stick with a simple approximation using the Taylor series. So let's crack on. Let us generate this within our assembly language. Then we will load it into our CPU and we will see it running. Now we don't need to talk too long about the code here because we've seen it previously with the sine and the cosine. It's just a different variation. So we're going to have on the right hand side the calling function. This time the calling function is the tangent, and we're going to work out the tan of 45 degrees, which should give us a value of 1. So this is the 45 degrees here in radians, and we're going to pass that into the tangent function. So let's have a look at the actual function, and I've made a little note of the Taylor series approximation. So this is the Taylor series approximation that we are using, and then I've written it in a simpler form. So all I've done is I've looked at the value of 3, so I've worked out 1 upon 3, which is 0.333, and the 2 divided by 15, which is 0.1333, and the 15 divided by 315, which is this number here. So everything just remains pretty much the same. This time we're going to work out the value of x here, and then we're going to have the x to the 3 divided by the value of 3, and then we're going to have the next term here and the term in x to the 7 here. So it works through and it generates the final result, and then the result is saved to the position called tangent within the calling function. So let's load this up and we will run it, and we will see whether we get the result, which should be a value of 1. So remember, it's going to be 1 in the fixed point number system, so it will actually be in our hex, it will be 0, 1, 0, 0. So I have loaded the subroutine into the ROM and the program into the RAM. Now let's run it. What I will do is I will pause the video here and I'll go to the end. It takes a couple of minutes to run through this. So that's the program finished. Let's have a look and we will see what the final answer is. Now we were expecting to get the answer 1, which would be 0, 1, 0, 0 in our fixed point number system. But we've ended up with 0, 0, FC. So we're a few digits out. So we've got to FC, so the next one would be FD, FE, FF, and then 1. So we're 4 values out. Now we're going to start losing accuracy with more values that we add in the Taylor series expansion, and these accuracies, the loss of accuracy is really due to the rounding. So this throws up some interesting questions. For example, we may find that if we were to use just the 3 terms, then as opposed to the 4 terms for the Taylor series approximation for the tan function, we might actually get a more accurate result. So let's have a look and we'll see at the actual value F00 FC and we'll see how far out we are. So I have run up the little conversion tool here. Now the answer we were expecting to get was 0100, which is a value of 1. Now the actual answer we got is 00FC, and that's 0.984375. So I will take a note of that number and we will look at the error percentages that we have here. So we have our tangent function in brown and our approximation in blue. So this is the first 4 terms of the Taylor series approximation to the tan function. Now we tried to generate it at 45 degrees. So 45 degrees is here. Now if we were to zoom in on this, then we're going to have 3 different points that we can look at. So the first point that we're going to look at here is the actual value. So the value we're expecting is a value of 1. Now the best we can hope for using the 4th order approximation is going to be a value of 0.9967. So in effect we've got 99.67 of the way percentage of the way there using the 4 values for our Taylor approximation. But the actual result that we get is down here. So the result we get is actually 0.9844. Now whenever you subtract this one here from this one, you get 1.23. So in effect we've lost 1.23% of accuracy running the actual algorithm due to rounding errors. So we're not too far out, 1%, it's reasonable for us, and I'm happy to keep this algorithm for the moment. And there are other ways of generating these algorithms. For example, we could run through the Chordic algorithm in order to generate this, and that's something we will look at, but not until the next course. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.